Unit 6 is all about heat and thermodynamics. A lot of these topics we've talked about before. Some of this builds on that kinetic molecular theory stuff that we've already talked a lot about. But we're going to get more in depth with enthalpies, which is breaking and making bonds, and things like that. So, the first thing we're going to talk about is that kinetic molecular theory idea that faster particles means higher temperatures. So when the particles move faster, they have more kinetic energy. And more kinetic energy means more heat. And more heat means a higher temperature. So higher temperature particles are moving faster. That's the big bold arrows, longer arrows. Low temperature particles are moving slower. And this all relates to kinetic energy. And then we define this as heat. So if you talk about heat, you're talking about the speed of the particles, the average speed of the particles. So if you put a pot of water on the stove before it's boiling, those particles are moving, they're in motion. But as the oven, stove, transfers its heat to the water, the particles start moving faster and faster and faster as the temperature goes up. Higher temperature, faster particles. That's why eventually the water boils, because the particles move faster and faster and faster until some of them start to escape, and then more of them escape, and eventually they're all escaping, and that's boiling. That's when you have the water vapor. It's all about the speed of the particles. Questions so far? Okay. This graph is important. We've seen this graph before. This is not new. But the number of particles, the energy of the particles, at a lower temperature, you have more low energy particles, less high energy particles. At a higher temperature, it's more spread out because you have more high energy particles. Same area under the curve. Let's say it's 100 particles. At the lower temperature, more of them have low energy. The higher temperature, more of them have higher energy. This graph will be on the test in some form. I don't know what the question will be. I don't know if it'll be multiple choice. I don't know if it will be free response. But some version of this graph and a question about it is always on the test. It's important. They care about this. Because this shows that you understand the energy of particles and how that relates to their temperature. And then how that relates to their activation energy and their likelihood of reacting. It all goes together. Unit 5 relates to Unit 6, and then 7, and 8, and 9. Questions? Okay, so heat transfer is the next thing I'm going to talk about. So let's say you have two blocks, one of them at 10 Kelvin and one of them at 20 Kelvin. Why am I measuring in Kelvin? Why does Kelvin make the most sense in terms of thermodynamics? Zero Kelvin is absolute zero. What happens at absolute zero? There's no motion. The particles stop moving. So absolute zero means no motion. And no motion means that the kinetic energy is zero. By definition, we've been talking about the faster the particles, the more kinetic energy, the higher the temperature, right? Those all go together. Faster particles, more kinetic energy, higher temperature. Zero kinetic energy, no motion, not moving, zero temperature. That's why Kelvin makes the most sense. If we're in Celsius, that's negative 273 degrees Celsius. Well, a negative temperature doesn't really mean a whole lot in terms of motion. If you had physics, doesn't mean they're moving backwards. So here we have to talk about Kelvin because it has meaning. 0 Kelvin, 0 motion, 0 temperature. 0 everything. Okay, so this block is at 10 Kelvin. This block is at 20 Kelvin. We bring them into contact. We let them touch. And what happens? Do they stay at 10 Kelvin and 20 Kelvin? No. What happens? Angelina? Heat transfers until they reach the same temperature. Where does it transfer from? High to low. Until they reach equilibrium, which in this case is the middle. Heat transfers from high energy to low energy. And that happens because when these things are brought into contact, these particles are moving faster, right? They're at a higher temperature. So these faster moving particles collide with these slower moving particles. When they collide, the faster particle slows down a little bit, the slower particle speeds up a little bit, and then you have two intermediate particles. And that happens over and over and over again until the collisions don't cause a change anymore. And then once the collisions don't cause a change anymore, we call that equilibrium. Where both blocks have the same average kinetic energy and therefore the same temperature, Kelvin. They only meet in the middle if a few things are true. What has to be true for them to meet in the middle? We're making assumptions here. What assumptions did I make?
The room temperature is 15 Kelvin.
We're making an assumption in this case that these are in a closed system, which means you're on the right track. No energy transfer to the surroundings. Or from the surroundings. Almost like our blocks are in a vacuum. There are no air particles around it to absorb energy or give energy. That's one. What else are we assuming? What if this block was bigger? Would they end up at 15? Where would they end up? I mean, you don't have to be exact. Higher than 15. So the masses of these blocks, the sizes of these blocks, have to be equal. You have to have the same number of particles of each. And then there's one other thing. What else are we assuming? What if this one is made of aluminum and this one is made of ice? Would the temperature be the same at the end? Would it all work out perfect? Right in the middle? No. This one would transfer heat more easily than this one, and then we would have a different temperature at the end. So it has to be a closed system. We're going to talk a lot for the rest of the semester until the AP test about closed systems. We have to ignore the surroundings. Now, eventually, not this year, but if you take college chemistry, upper level college chemistry, if you're an engineer, you can't ignore the surroundings anymore. But for us, for our purposes, we're ignoring the surroundings. We're going to pretend we're in a closed system. We have to assume that they're the same size, otherwise the math is different. And we have to assume they're the same material. Okay, tomorrow all of this is going to lead us to calorimetry and specific heat. And we did that in Chem 1A, but we're going to go more in depth tomorrow. Questions? Okay, that's it for today.